This is a reading of Written in Bone, Buried Lives in Jamestown by Sally Walker, Chapter 6, Part 3. The first picture on page 76 shows, the caption says, "This cross section is a diagram of the stratigraphy of the grave shafts and the surrounding soils. To bury the too large coffin, the diggers dug a big pit. They put coffin 1 and coffin 2 in it. These coffins were covered with soil layer 3, then layer 2, and then finally layer 1. When the small coffin was buried, a pit was dug through layers 1 and 2 until the diggers hit the middle coffin. It and the small coffin were covered by soil layer 7. Sometime later, the workers apparently dug up the small coffin, wrapped it in lead, and returned it to the grave pit. Layer 8 is from this second burial." On page 77, the picture's caption says, "The lead coffins at St. Mary's were scanned with special waves of colored light above. The colored lights have different wavelengths. They can be used to bring out details or stains that are otherwise invisible. The team was looking for special markings, safe treatments the on the coffins, and cracks in the lead. None were found." Okay, let's read the text. The archaeologists began the excavation by removing backfill soil to expose the head ends of the 3 coffins. They were interested not just in the coffins, but also the wall of undisturbed soil left behind after the backfill had been removed. The soil became the object of investigation of geologist Gerald Johnson. Johnson specializes in stratigraphy, a branch of geology that deals with understanding how soil and rock layers and the features found within them are arranged. It explains the order in which layers and features form and how they change when the soil is disturbed. Stratigraphy can provide critical information about the timing and nature of such changes, helping archaeologists to analyze their findings. Stratigraphy of the undisturbed wall of soil told Johnson an interesting story. He clearly saw the outline of a grave shaft that had been dug wide enough for two large coffins to be buried in it side by side and at the same depth. That meant they had been buried at the same time. But changes in the soil color and texture also told Johnson that sometime after the burial, this large grave shaft had been disturbed. The shape of the disturbed area cut down directly through the soil that had been used to fill the large shaft. The tiny coffin lay at the bottom of the disturbed area. Thus, Johnson could tell that this tiny coffin had been buried after the 2 large coffins. The next step was to attempt to retrieve an air sample from the coffins, a tricky undertaking. Opening a coffin would immediately corrupt the air it contained. Without the correct preparation, a drill or any other instrument inserted into the coffin would break the coffin's airtight seal and let modern air enter the coffin. Nor could the team drill a hole into a random part of a coffin to obtain a sample. The tool might damage the human remains inside. Before proceeding further, the team had to know exactly how these coffins were constructed and where the remains lay. In other words, they need a way to see inside the coffin without opening them. An X-ray is one of the first tools that scientists use in such a situation. In this case, that wouldn't be possible because conventional X-rays can't penetrate lead. Fortunately, the team had anticipated and solved this problem during their planning period by building a small lead coffin for testing purposes. Nuclear physicist Mark Moore experimented with techniques similar to X-ray to find one that could see through lead. The experiment showed that another type of ray, called a gamma ray, easily penetrated the experimental coffin's lead sides. Like X-rays, gamma rays can be used to create an image. Based on successful trials with the experimental coffin, the team decided to examine the project's coffins with this technique. In small measurable amounts, gamma rays are helpful in treating certain kinds of cancer, but uncontrolled amounts are very dangerous. They can cause serious illness. To protect people from this risk, Maryland state inspectors required the team to build a protective wall around the coffins before they used the gamma rays. The safe wall contains more than 600 large sacks of sand. Next, the team put special photographic paper along of the head one side of the head end of each coffin. The instrument that produced the gamma rays was placed on the other side. It directed a short burst of gamma rays toward each coffin. Different materials, for example, lead, wood, or bone, absorb different amounts of gamma rays. Lead absorbs a lot of gamma rays. As the coffin absorbed the rays, the lead appeared as a light area on the gamma ray image, much like a person's bones show brightly on an X-ray image. Air, on the other hand, absorbs few gamma rays. The rays that passed through the air-filled spaces inside the coffins created dark areas on the image. The images revealed that each set of remains was actually contained in two coffins. The outer coffin had been constructed around an inner coffin made of wood. The remains lay inside the wood coffins. Unfortunately, the images also showed that the small and medium-sized coffin did not appear to be sealed tightly shut. In fact, the team could see that the medium-sized coffin's rope handles had rotted, leaving holes that permitted air to enter the coffin. However, the largest coffin seemed to be tightly sealed. The team hoped that meant it might contain preserved 17th century air. The team decided to sample the air from the large coffin using a special tool, a drill with an air hose attached, Mark Moore designed. The gamma ray image had revealed an empty area in the coffin, so the team knew that drilling into that area wouldn't damage the contents. But sampling the coffin air was still tricky. Even the tiniest hole drilled into the coffin would let modern air inside and contaminate the coffin air. Again, the team was ready with a plan. Using Moore's drill and a hose tool, they slowly bored partway into the lead and stopped. The scientists used a vacuum pump to remove all the air from the hose. When the hose was completely air-free, they resumed drilling the rest of the way into the coffin. To make sure the hose was removing only uncontaminated coffin air, the team needed a way to detect any changes in air pressure. Such a change would indicate that the coffin's airtight seal had broken and that air outside was flowing into the coffin. Think of sucking liquid from a juice box. As you drink, you vacuum juice and air from the box. That reduces the air pressure inside the box. The pressure of the air on the outside becomes greater than the air pressure inside, causing the sides of the box to collapse inward. If you then suck a pin in the box, outside air would flow through. If you stuck a pin in the box, outside air would flow in through the hole, raising the air pressure inside the box. That increase would be strong enough to push the sides of the box back to their normal position. To measure the air pressure inside the coffin, the scientists connected an air pressure gauge to the air hose. The monitor on the gauge would reflect any changes in the coffin's air pressure. As the team removed air from the coffin, the monitor remained at a constant level, indicating no modern air from outside the coffin was seeping in. This support This supported the team's belief that the coffin was airtight. They transferred coffin air into sealed containers, which were sent to a laboratory for analysis. For a while, the air pressure in the coffin remained stable, but eventually the seal loosened. The coffin held the seal for about 3 hours, then started letting go, said Miller. The pressure gauge monitor showed that outside air containing oxygen was seeping in. Oxygen gas reacts with many substances, including human remains. In 1799, when the medical students unsealed Anne Copley's coffin, they reported that her body, hair, and burial clothing were still well preserved. But as soon as the students opened her coffin, oxygen reacted with her flesh, hair, and clothing, causing ruinous results. The students reported that within a few hours, the clothing and flesh had crumbled to bits. 200 years later, when the project led coffin team reopened the coffin, no traces of fabric remained. Of course, Miller and Riordan had no intentions of allowing the remains inside their lead coffins to disintegrate. During their preparations, they had developed a solution to the oxygen problem. First, the team stopped the inflowing gas. Next step was to replace the oxygen with an inert gas called argon. Inert gases do not react with other substances. They do not contribute to decomposition. While the coffin had laid buried below the surface, their contents were the same temperature as the soil surrounding them, about 50 to 60 degrees Fahrenheit, 10 to 16 degrees Celsius. As the team excavated, however, the lights they used for visibility had heated the air, causing the temperature increase around the grave shaft about 10 degrees Fahrenheit, 6 degrees Celsius. That increase would also raise the temperature of the argon. Even though argon is inert, the additional warmth from the gas might have posed a threat to the remains. Again, the team was ready with a solution, but this one did not require any cutting edge technology. They simply filled a picnic cooler with ice. Before they pumped the argon gas into the coffins, they channeled it chilling it to the same temperature as the soil that surrounded the coffins. Through this method, the team protected the remains in all three coffins from further decomposition. The last step before they removed the soil wall that still surrounded the foot ends of the three coffins was to make a record called a soil peel. Gerald Johnson treated the wall with a sticky substance called resin. Then he smoothed a layer of cheesecloth over the resin, covering the entire exposed soil surface. He applied a coat of resin to the cloth and topped that with another layer of cloth. After the resin dried, Johnson peeled the cloth from the wall. The soil that had formed the face of the wall was stuck to the resin, creating an exact copy of the soil layers. The soil peel was stored at the St. Mary's City Laboratory so that it could be consulted for further questions arose concerning the stratigraphy of the grave. Okay, let's just go back a little bit. Look at the pictures. Page 78. This gamma ray image above is the medium-sized coffin. It shows a skull, the nails and wood grain of the inner coffin, and the lead sheets of the outer coffin. This coffin was no longer airtight. Page 79, it says, the largest coffin was still airtight. The team hoped it would be able to get a sample of the 17th century air without disturbing the coffin's tight seal. The air sampling was transferred to a lab for further study. Let's go to page 80. The team didn't want deterioration to happen to the lead coffin people. To avoid any degradation, the team members pumped neutral argon gas into the coffins above, which doesn't interact as oxygen can. To make the soil peel, Gerald Johnson first paints resin onto the soil wall above. After removing the soil peel below, Johnson placed it on a plywood board to support it as he and his colleagues lifted the peel from the grave shaft. The cheesecloth is visible along the edges of the peel. Okay. Um, so the picture on page 82 says, moving the lead coffins was no easy task. The team came up with elaborate methods for lifting them from the site and moving them to the lab. And on page 83, it says specialists begin the job of examining the lead coffin remains in the ultra clean lab set up in the U.S. Army Field Hospital tent. The text says, to the clean room. In a typical excavation, the next step after exposing remains is to undertake in situ examination. But nothing was typical about this situation. The size of the grave shaft and the conditions at the site made an in situ examination of the coffin's contents impossible. The coffins would have to be moved from the grave before they were opened. The team prepared for this step by testing the strength of each coffin to ensure that it could be moved safely. The coffins were scanned with infrared light, a type of light that allows scientists to see how metal retains and loses heat. After heating the coffin surfaces slightly, the scientists watched the metal cool under the infrared light. Areas that contained cracks cool at a different rate than undamaged metal, making the cracks readily visible under infrared light. If the coffins contained cracks, the lifting process could place enough stress on the lead to widen them. The coffins might break into pieces. Fortunately, the infrared light revealed no cracks. Lifting the lead coffins, the largest weighed almost 1,500 pounds, 680 kilograms, was a formidable task. Mathematicians used special instruments to calculate the thickness of the lead. From those calculations, they determined each coffin's weight. To raise the coffins in the safest possible way, the team decided to lift them on metal plates, starting with the baby's coffin, positioned alongside it a hydraulic jack. Gently pushed a rectangular plate into the soil a few inches below the coffin. The layer of soil beneath the plate and coffin served as a cushion. The jack slowly pulled the little coffin away from the medium-sized coffin. A micro crane lifted the plate and coffin up and out of the grave. As soon as each coffin had been safely lifted from the grave shaft, it was taken to a clean room, a spotless, clean laboratory area. The clean room at this site was a U.S. Army surgical field tent that had been specially set up in the field near the chapel's foundation. Inside the tent, Doug Olsey, Carrie Brewelhide, archaeologists, conservators, and medical personnel analyzed and sampled the remains for further scientific analysis. What they found amazed and puzzled them.